Yeah, Mr. Tripathi, can you hear me?
Yes, sir. Sorry, you're audible.
Yeah, thanks.
Hey, Shankar, you are the moderator now.
Yes, Professor. I think I'm just waiting. Shall we start or
No, you can wait.
for...
You can wait. You can just give general instructions. At least the speakers are there.
Okay.
We can wait for some time, maybe 2 minutes more. Yeah, the duration is ending. It has been 1 or 2 minutes, so it's coming down.
So this is Shankar from IIT Bombay. So I see Masaaki-san, Dr. Gharpure, and Mr. Käufeler. So we have about 15 minutes of presentation, and we collect the question and answers in a Google Sheet, and then after all the 3 presentations are completed, we'll go through the questions. I think, Priyam, are you here? Yeah, that's what I was.
Yes, sir, I'm here.
So I think link to the Google Sheet is there in the chat box now. Is that right, Priyam?
Yes, sir. This is the link.
Yeah. Okay.
Yeah, for all the participants, if you have some questions related to the presentations from the speakers, please put those questions in the provided link so that after the session completes, essentially after the speakers complete their presentations, we'll go through those questions based on the time availability. All of them or at least some of them. Priyam, is it time to get started or should we wait because it's already 3:42?
We'll get started.
So we can start.
Yeah. Okay. Welcome to the residential and workplace cooling breakout session. This is session A, and we have 3 speakers from Japan, India, and UK. So the first is Mr. Ebina Masaaki-san, and hello. Then followed by Dr. Praful Gharpure from India, and followed the final speaker being Mr. Matthew Käufeler from UK. And I request the first presenter, Masaaki-san, to present first. To introduce him, he is the chair of Japan panel of the IMechE. He's a chartered engineer and is a certified welding engineer as well. And he wears a lot of hats. I can see a lot of experience listed, and he heads the Japan International Cooperation Agency project related to gas sector in Bangladesh. And he started as an engineer, mechanical engineer, and his work spans about 40 years, especially in the oil and gas industries. And his roles include quality control, process safety management in oil and gas facility operations, and also some corporate. So his concerns primarily are towards the environmental programs in the oil and gas industry, including toxic spent catalyst disposal and emission from oil and gas facilities, energy savings program, and so on. So I request Masaaki-san to present his slides, or if you want, I can also share. please let me know.
Thank you for the introduction.
We can see the presentation now.
Yeah. Okay. Yeah. Well, thank you for the introduction. My name is Mr. Ebina, and it's a great pleasure to be able to communicate with the people in India and the UK. My presentation today is about the LNG cold energy utilization based on the experience in Japan. I am just starting with the general image of the LNG or natural gas. In general, in comparison with the coal and oil, natural gas is regarded as a clean fuel. Something shown here, the CO2 emission or NOx or SOx or whatever is regarded as a clean. And especially for the LNG, it's basically methane is the major component out from the many other hydrocarbon fractions. And how the LNG is produced is the original gas contains a lot of impurities and heavy fractions. And first, the heavy fraction is removed, and the acid gas, H2S or CO2 impurity is removed, and the LPG fraction is recovered, and sometimes the ethane is also recovered. After those recovery, the fluid is dehydrated, and the mercury removal system through those system, then LNG liquefaction is started. So before going to become LNG, lots of the process need to be done. And the gas itself is also differ from the gas field to field. This is the indication of the CO2 concentration in the original gas. In Australia, more than 10% of the more fraction of the gas, its CO2 is included. And those need to be re-injected in the ground. But in some cases, those gases, CO2, are emitted to atmosphere in the old LNG plant. And this is the one of the typical LNG manufacturing process. Quite significant part is taken by pre-treatment, and the LNG portion is this much. This is the transportation efficiency of the natural gas pipeline, 90 to 80%, 85%. What happened to those gap is consumed as the fuel for gas compressor, and the heat would be dissipated in the atmosphere. LNG, in case of LNG, is a little more gas treatment, liquefaction plant, and the transportation. If you consider all of those, the actual energy is 75% to 70%. And the after treating of the gas, what to do, how much energy to be consumed to liquefy the gas. This is as I show here. 2,900 kilojoule per kilogram LNG is required to liquefy the LNG. And out from the 2070, it's about 30%, 70%. It's dissipated to atmosphere as a heat in the process of the liquefaction. So remaining 30%, 830 is available as a cold heat. So if you think about all of those chain, the available amount of the cold heat is not as much as what we have expected. But this amount is also very big. Japan had many trial in the recovering the cold heat from LNG, as listed here. This is the air separation unit, and the use of the LNG is shown here, and the amount of the production capacity of the liquefied nitrogen, oxygen, argon, or whatever. This is the list of the air separation unit, which uses LNG cold heat. For your information, by using the LNG cold heat, 50% of the electric power consumption is saved. So very much benefit for those air separation unit. Power recovery is another area with the use of the LNG in the process of the vaporization. Energy is recovered, something like in this table. This is the list of the power generation now in operation in Japan. Another major area is the liquefied CO2. This is something to do with the cold chain. Some of them are used for dry ice, and the liquefied CO2 is a very good cooling method for the food industry or medical area. As I show here, the energy potential is 830 kilojoule per kilogram LNG, and those energy is to be utilized in the form of the cold heat or volume increase. The volume increase ratio is about 600 times than in comparison with the liquid phase. And as I showed in the previous slides, electric power or air separation, liquefied CO2, and some others what I am also talking about in this session. Electric power recovery. As you see, the LNG stream is in the color of the blue and the green. After vaporize, then LNG, gaseous LNG, is goes through the heater. It's by seawater, warmed up by seawater, and then lead to the vehicle expander, then to the gas grid. While the propan is used as a intermediate medium circulating, and this is called Rankine cycle. And well, the propane liquefied boost up by pump and through the vaporizer by seawater, then injected to the expander. And it's again cool down by LNG. This with this cycle, then the typical of the banking cycle. I think some of them are very much familiar with this. Gas turbine is generally usually rated at the temperature of the 15 degrees centigrade. However, when the air temperature is goes up, then efficiency is going down. If in case of the Japan or India, summertime of the temperature is quite high, then the performance of the compressor will be down from the 100% to the 82% if the ambient temperature is 40 degrees centigrade. And so the very much benefit if you install the air intake chiller. This is the courtesy of the OSA gas, and you can see the chiller. Size of chiller is very, very large, but it's worth to install because of the enhanced efficiency. This is the case of the CO2 liquefaction plant. If you have a refinery next door, refinery uses a hydrogen plant. Hydrogen plant, as a side product, they also produce CO2, and the CO2 in general to be released to atmosphere. But this CO2 can be recovered, and if the LNG is available, it's very much easy to manufacture liquefied CO2 and also the dry ice. And the benefit is much energy saving if the energy used, and also the size of the performance of the compressor will be improved by installing pre-cooling system. And this is the one of the another example. If the other chemical companies nearby, you can integrate the system. This is the case of the OSA gas, and the nearby they have a Mitsui chemical company who manufacture ethylene. And the combining the process configuration with the those chemical company, and the in the long run, by this combination, it's their cold heat recovery is almost achieving 100%. So we are not better not to look at the just a recovery of the power, but we we need to look at the adjacent industry, how they are using the heat, and how the cold heat can be contributed. This kind of the thinking may be very much necessary. And in the end, just the my kind of proposal is that they review the existing energy terminal and find potential of the energy saving, find appropriate fund for further study, and consider applying for the carbon credit mechanism, because this is the additional revenue to support the project, and then implement the project. Well, this is all about myself. Thank you for the attention.
Thank you very much, Masaaki-san. This is a very detailed presentation. Thanks for the presentation. We'll wait till the end to discuss some of the questions you may have.
Yeah.
Dr. Praful, can you please share your slides? Or yeah, we can see your slides. We can't hear you. Hello?
Yeah, is it better now?
Yeah, it is better, definitely. Yeah.
Yeah. So greetings of the day to everyone. It's a pleasure.
Let me introduce you. I just wanted to have the slides up. Now we'll have Dr. Praful Gharpure. He's a senior consultant at Tata Consultancy Services, and he's part of the infrastructure planning and development. And he has been an architect, urban planner for over 25 years now, and he has been associated with a number of projects that span from architecture, planning, management consultancy, and IT services delivery. And he has led a number of teams on master plans, process improvement studies, feasibility studies for tourism, urban development, along with projects on IT enablement for citizen-centric services. He has published more than 30 papers covering all these different aspects that he had worked on. And he has a PhD from CEPT University in Ahmedabad, and a master's degree from the same place, and bachelor's in architecture from BRC Nagpur. And he is also a PMP, a project management professional, certified professional. And also he's a Six Sigma Black Belt certified practitioner. So I request Dr. Praful Gharpure to present his work on climate resilience.
Yeah, thanks for the long introduction. It's a pleasure to be part of this forum and the session on the residential and workplace cooling under the larger context of this workshop, that is the climate resilience. And I would like to bring in the architect's view in this forum of engineers, so that there is some element of design we discuss from the building standpoint. So to set the context of my talk, as we discussed initiatives like these, there are some upfront questions from our users, the end users from whom we are working in consultancy capacity. So first of all, we have been asked like what this all initiatives are all about, and as it was elaborately mentioned in the plenary talks, that we have to minimize the effect of the factors on the environment, and that's why these initiatives are thought about. And why we are, in the context of this session, why this cooling is emphasized, as this has also been brought out, that it is the most power consuming segment in the building industry, as well as the use of the conventional compressor based cooling, leading to the refrigerants causing impact on the environment. And the last question is asked, like, how we are going to do it. And now it has been, now we have reached to a stage that every one of us have to contribute their bit in order to save the impact on the environment of whatever bit we can do. So all these initiatives which are getting covered, everyone has a role to play, and to prevent this planet from experiencing irreversible changes in the decades to come. And in the context of this talk, why we need cooling, why we are talking about cooling in the first place, that is the prime reason is that most of the time all the users are indoors. And when a person is indoors, they need to have not necessarily cooling, but they need to have a comfort environment. That comes from the concept of ventilation as well as the well-lit places to be bare minimum about the comfort conditions. So we talked about the power consumption in these. So when we see the overall workplaces consumption of power, we see the percentage here on the left-hand side of the graph. The buildings and household together are consuming 50% of the power. And if we break it down further, the cooling itself is taking more than 60%, and the lighting and the ventilation part. So majority of the power is coming from the various measures we are taking for comfort conditions enhancement in the building envelope we are residing. So when we see a residential segment, we are seeing a lot of changes in the lifestyle with the use of gadgets, but this has been adequately addressed with the star rated equipments coming in the market, and this is reasonably getting addressed. But what we need to see times ahead, the graph on the right hand side shows the extent of increase which is likely in India for the use of air conditioners, which is 5% today. It is going to go many-fold in another 2 decades from now. So energy use is of a prime focus in this area of building environment, and it has to be properly addressed by various mechanisms, which some of them we are going to see in this talk. So when we are talking about workplace is basically a very wide term, and workplace is a place where a occupant is spending 8 to 10 hours of his time during the day for his workplace, for his day-to-day work. So there is a demand for making his stay in that particular place comfortable. And the workspace varies. So I have tried to list down some of the building segments, and each of these segments warrant different conditions of comfort from the user's standpoint. So there is a primary focus on defining a user, defining a workplace, and then defining the demand for the cooling, which will go into various designs, and that gets executed. At the same time, we also have to address the processes which these buildings house, and also the functional needs of certain equipments which warrant for certain degree of temperatures, which can be given only by mechanical means of cooling. So all these aspects need to be thought of in designing the workplaces, and it varies from segment to segment, and we'll see in the later part of the presentation. Now, when we are talking about cooling, I'm talking about 4 C's. Now, first of the thing is, we are not talking about air-conditioned spaces. We are talking about comfort within the enclosed spaces. So these are the parameters, the first C component, that is the various comfort parameters that go into a building design. And these drive the need for the technology and based on the type of the space we are considering, and that determines the cost. And based on these 2 first and second C's, we decide the channel for distribution of the cooling which is going into the building. And fourth of not but not least, the compliance to the standards, which also was emphasized in the earlier sessions in this particular event. So all in all, it takes some basic measures which need to go in any building envelope which is put to use for occupancy. So first is the regulated airflow, and now in today's COVID context, the filtration is also of an importance. Then second is the balance between the temperature and humidity, that is well-known fact. But the third thing is active air balance in all the indoor spaces. So all pockets of the floors which are getting conditioned has to have a proper airflow. And the fourth one is to have a proper air change, to have a contaminated air taken out from the enclosed space and the fresh air is put in. And last but not the least, whatever the parameters are set are to be monitored. Now, how do we do all these? I have tried to put up a simple, easy to understand framework. I call it as a 4M framework. And all these 4Ms have got a different dimension, which we are going to see in the subsequent slides. The first of the 4Ms is the magnitude. So what magnitude of building we are looking at from a cooling standpoint? That is the first M. Second, as we saw the various building segments, which are the modules within a building which we need to address with the cooling requirement? That's the second part. The third part is based on the magnitude and the modules of the building, what measures we need to take to have an effective comfort conditions within the building to have a user satisfaction. And fourth, when the building is put to operations, how do we monitor the performance of the building as well as the equipments that go in? Now, having said that, we will see the first M out of the 4Ms, that's the magnitude. Now let's gauge the magnitude of the requirement itself. Now this graphics is for the city of Bombay. As you see over the decades, this red portion in the graphic is increasing. What it indicates is that we are building up the spaces as and when available, and I'm sure the next 2022 one, which will come after the next census, it will be still worse. So what it is indicating is on the table on the right hand side is the potential built up space that is going to be added in our cities in next 2 decades is phenomenal. And all these are going to have 70% of this thing is going to require the cooling, as well as 50% may require the mechanical air conditioning. And of course, the commercial air conditioning demand is going to go almost 5 times. Those are the projections which are given. So what it is of prime importance other than the buildings is the surroundings. Now we have to have a very serious thought on the surrounding spaces in relation to this graphic is, as per the standards, we need to have 10 to 12 square meters per person as the open space in a city. But we are having, it is much lesser, as the graphics says it all. So we need to have a conscious effort in maintaining our open spaces which are surrounding the buildings, which have equal importance on the cooling aspect of the building. Now this, another dimension of the magnitude I touched upon is the high volume of the airspace that gets contained into the building envelope, how we are treating them, using the variations of the floor plates, which I mentioned about the building segments. So for example, if we have a hospital building, hospital may have various segments, like we have a reception, we have got OPD, we have got consulting rooms, we have got wards, we have got operation theaters, we have got laboratories, we have got medicine storage units. All the things, all the requirements of cooling of all these areas are different. If these are logically grouped on a floor plate, then we have an optimization of all the MEP services in a building. Then the choice of the material, the extent of the glass used in the building, and those are the things also design features that go in. Also the site conditions, whether the buildings are rightly abutting the road or they are having a surrounding space which can be treated. So the typology is also important. Now these are some of the modules which I just mentioned. These modules are nothing but the spaces within the building complex, how they are grouped logically, and to have with respect to the optimization of the mechanical services that go into it, be it air conditioning, be it plumbing, be it firefighting, be it electrical services. So optimization of the floor plate, like the space layout optimization, is one of the key factors in the design stage itself. Then some of the yardsticks, like the floor plate aspect ratio, this has to go with the orientation. We are going to see it in detail. Then the wall to window ratio, the open to built up space ratio, and the glass area proportion. These are another things. The second M is basically to club the functional areas logically to have optimization of these services. Now comes to the third M, that is the measures. Now here we are going to see one case. This is of an office complex here. It has a rectangular plot, and the longer side is facing east-west, and the shorter side is facing north-south. So if you see the orientation of all these blocks are basically oriented with a shorter side facing the east-west. So and then further on the two ends, the north and south end, we have got the service course, which are mentioned, shown in the orange boxes in this graphic. So these are basically shielding the area so that we don't have a direct sun during any part of the year on this particular cool space work areas. Further on these blue blocks, one side is the passage, thereby another walkway is created so that you have another shielding. So glass facade is controlled only on one side. So what it helps, you see the grouping of these buildings is in such a way that it formulates shadow of one building over the another. So it is preventing all the majority of the cooling areas which require air conditioning to be shielded. Thereby the cooling load is drastically reduced. Then treating the external areas around the buildings, we see we have got these grass pavers and with the water percolation mechanism there. So this also reduces the heat island effect in the overall surrounding spaces. Then, as I said, we have controlled the use of glass facade, and thereby using the double glaze unit, we are further reducing the heat gain inside the building. And the complex is such a way designed that you have a breeze flowing in, and you see these blocks are connected through interconnecting lobby where there is no air conditioning. And this airflow is channelized through these blocks, and the block corridors are converted in such a way that you have this breeze which can flow in, but it cuts the direct sun. So these are some of the measures which are taken in the design stage itself. And you see all the terraces are properly treated so that you have got a good 6 to 7 degree drop from the sun which is exposed to the terrace. So these are the things which were taken in the design stage itself. And now we see when this is put to operations, what happens. Now, when it is put to operation, it is full of various equipments. Now, it is ensured that the usage, all these equipments are in a modular fashion. And all these are connected to the central building management system. And what this building management system actually does is it captures the building data from the access management system so that we know at any point of time in any building, in any corner of the campus, how much is the occupancy and how much is the temperatures inside the building and the surrounding. Accordingly, the preconditions are assigned and the optimal setting computations are done, and then the equipment is run in that fashion. So what it gives us is the zone by zone comfort settings, the energy consumption by each of the building block for performance measures, occupant density and asset availability and asset maintenance also is ensured by that. So in the earlier slide, we saw the measures which went into design stage that itself gave a design load reduction of about 15 to 20%. And here during the operations, we see another saving of energy savings of another 8 to 10%. So this way, if we optimize the use of these spaces as well as the equipment, we have got a good potential to have an energy saving right up to 30-40%. And here I have not mentioned anything about solar or any other thing, which once added, that will give us still more a path forward towards a net zero building. Now, the measure summary quickly go through. When we have these buildings functional, the air changes are maintained, the CO2 levels are monitored electronically, fresh air provision is done whenever these thresholds are reached. CFMs are ensured in all the pockets of the various buildings spaces, temperature to suit the user requirement, the air inflow with the UV treatment as well as the filtration to avoid particulate matter, provision of daylight occupancy sensors to reduce the lighting load based on the conditions around the building. Renewable energy, of course, that is another thing to aim at the net positive. The complex also has a rainwater harvesting as well as the zero discharge facility. So everything is treated at the site and nothing goes out. So this is another simulation. Like if you see on the first column, if there's only manual control, we don't see any reduction in the saving of the lighting. But if we have the occupancy sensor and the daylight sensor, this can go right up to 50 to 60% of saving of the lighting expenditure on the in the building areas. This is of course related to the daylight functioning of the building. Now, how do we monitor the results? Like I mentioned about the treating of the terrace, treating of the glass facade. Then there is an option of creating a evaporative cooling system within the campus if at a later date. But this also has a potential to save a significant amount of power. And as well as it will give a fresh air inlet in the building, considering the current times of the pandemic, which is we have just passed through. The equipment controls, I mentioned about the VRVs, the VAVs, these things are also optimizing the airflow, thereby reducing the load on the equipment and thereby giving us energy efficiency. So all these together have got another potential of saving another good significant amount of energy from the building performance. So having said that, we have to move a little bit away from the buildings as well. So we need to treat our surroundings also. And so the landscape and the building surroundings, the magnitude of this can be seen from this graphic itself, that one mature tree is good enough for equivalent of a 10-room air conditioners. And then this is another example on the left-hand side is about converting a cycle track with a solar panel cover so that solar energy is used for the street lighting and can save the energy bill for the street lighting expenditure, which the authority is normally doing. And all in all these initiatives, if we see, there is a potential of reduction of good to 50 to 75 terawatt hours if we initiate such actions in this. And all these things, if we put together in a linkages, if you see, it improves the viability of this space. So when we are talking about workspaces, these are prime real estate which we are handling. As such, the comfort conditions, if they are met properly, the viability of the usage of the space is also very much. If you see, all the left-hand side parameters are fulfilling with the linkage on the right-hand side. This improved floor plate viability is one criteria that gets fulfilled. So having said that, once such a building performs, there are different agencies which assess these quantified results, and these ratings are provided. And of course, there's another thing which is coming up, like buildings are now need to be healthy as well. So there is a Well Building Institute that also gives a wellness rating to the buildings as well. So other than the green buildings, we have the healthy buildings as well as the concept that is coming out. Now, all these what we just mentioned or we must just touched upon for the interest of time is contributing to the our initiatives aligning to the SDG goals. So there are 17 SDG goals which the nations are committed, and in the space of air conditioning and workplace cooling, these are aligning to 6 of them. I'm not going to read all these in the interest of time, but these also complement to the nationwide initiative of the SDG matrix that is getting prepared at every state level, which is maintained. Last but not the least, this graphic is of a facade. We don't want to see our facades like these, but each outdoor unit here is shelling out at least 3 to 7 liters of water, and that water also needs to be channelized properly, which is currently going down the drain. So such parameters like also need to be looked into by the users community and the maintenance staff as well. And as we are talking about the office space, the graphic on the right hand side is also 1 email contributes to 1 gram of carbon dioxide we are producing. So several emails like these, if we contain, so our working mechanism is also equally important to maintain certain balance in the climate related initiatives. So that's pretty much I had for the time allotted, and my coordinates are on this slide for any questions in either in the session as well as or from the later part. Anybody can reach out to us. Yeah, thanks for the opportunity to give a talk here. Thanks.
Thank you for the presentation. In the interest of time, let me move to Sir Matthew next. Can you please bring up your slides? Mr. Matthew, we can see the slides. Let me do a speaker introduction. Mr. Matthew studied mechanical engineering and from Imperial College London, and he continued to masters as well, and he had been working in a cooling hardware manufacturer, and currently he works with Future Facilities, and he's a specialist in simulation of data centers and electronic equipment. And so I would request Mr. Matthew Käufeler to give us his views on data center.
Thank you very much for that introduction. Can you hear me okay?
Yeah, very clear. Yeah, it's very clear now.
Perfect. Okay, so thank you for that introduction. And also thank you obviously to our preceding speakers for their insights, and to our hosts for inviting me to speak today. I'll be presenting today on the topic of data center cooling in the context of increasing temperatures, heat waves, and heat island effects. And I'll start with an overview of the data center industry for some context, and then move on to discussing challenges and some of the potential solutions and opportunities in data center cooling related to increasing temperatures. So data centers house the IT systems that are used throughout the modern economy. I think they're typically imagined to be the preserve of big tech companies running websites and applications, but in reality, they actually support a wide range of economic sectors, including offices, factories, logistics and transport, telecommunications, esports, and financial markets. And as such, they're an extension of the physical workplaces that are occupied by those businesses and their staff. And just like the businesses that rely on them, the data centers range in size from small on-site server rooms that would use maybe tens of kilowatts of power, up to what we refer to as hyperscale facilities, which would use tens of megawatts of power. So the useful output of the data centers are essentially the computing services that they provide, that are provided by the IT systems that they house. And of course, those IT systems need shelter, they need power, they need communications networks, and they need cooling systems to operate. So we have to provide inputs of information, power, water, and of course the materials to actually construct the IT equipment and support the hardware, as well as materials to construct the building itself, in order to enable those IT systems to provide the computing services. And as with any system, alongside the useful outgoing information, we have waste streams. We have heat waste streams, wastewater, and end-of-life waste as well. Now, I'll be focusing on cooling systems today, which serve the IT equipment, the power distribution systems, and also the personnel operating the site. And they use power and water and, of course, construction materials, and they eject heat, wastewater, and eventually end-of-life waste. But first, we'll take a quick look at the industry's sustainability response to climate change concerns. So the industry has tended to stay a step ahead of regulators through self-driven initiatives. Atrey, the American Society of Heating, Refrigeration and Air Conditioning Engineers, published guidelines for thermal conditions in data centers, which are very widely used to determine the operating point of data center cooling systems. And over the years, they've continuously adjusted these in collaboration with IT equipment manufacturers, typically widening the limits for temperature and humidity to help data center operators to use less energy and water. The Green Grid, an association of professionals from the industry, have introduced key performance indicators to compare data center efficiency in terms of power use and water use, which have been widely adopted. These are based on evaluating the total data center power use relative to the IT system power use in the case of power usage effectiveness, and the total data center water use relative to IT system energy use in the case of water use effectiveness. Now, power usage effectiveness has been particularly successful and widely adopted, so much so that it's been taken on by the International Standards Organization as part of ISO IEC 30134. And a section covering water usage effectiveness is also under development for that series of standards. So with power usage effectiveness, a value of 1 implies that a data center uses no energy on top of its IT power use, which realistically is, I think it's fair to say it's an unachievable idealized value. And then higher values of power usage effectiveness imply higher levels of power use on top of the IT. So since it was introduced as a metric, the industry's moved from a mean power usage effectiveness of around 2.5 down to 1.6, and newly built facilities typically target power usage effectiveness between 1.1 and 1.4. So that's a reduction from 150% power use on top of the IT power use to now an overhead of only around 10 to 40% on top of the IT power use. And that means that despite ever-growing IT power use, the industry has actually managed to maintain a fairly constant level of total power use in the past decade through improved efficiency, which is, I would argue, quite an impressive achievement. And there are also numerous voluntary standards and scoring systems. Of particular note is EN 5600, which is a standard for data center best practices in which energy management and environmental viability are a key factor. And the EN 5600 series is also now in the process of being adopted as an ISO standard, ISO IEC TS 22237. So to achieve these improvements, the data center industry has had to pursue energy reduction strategies. And some of these have been relatively easy, such as segregating cold and hot air to ensure cooled air gets to IT equipment without being warmed up, and replacement of AC motors with more efficient electronically commutated motors. Pursuing lower energy use has also involved adoption of different cooling technologies to reduce the use of more energy-intensive refrigerant-based cooling. So some examples are direct fresh air ventilation, which avoids use of refrigerant compressors and chilled water pumps, which is also achieved by air-to-air heat exchangers. And then also liquid-to-air heat exchangers, which avoid the use of compressors and refrigerants by rejecting heat from chilled water directly to the air, rather than relying on a vapor cycle in between. And all of these can be aided through the use of adiabatic cooling or evaporative cooling, as the preceding speaker mentioned. And the image opposite is actually of a site. The image on the right is actually of a site in the UK that we at Future Facilities have worked with, where they use air-to-air heat exchangers and adiabatic cooling for the entire cooling system of their multi-megawatt data center, with no refrigerant-based cooling at all. But that isn't really the norm to use them in isolation. Often the refrigerant-based cooling is retained as a backup option, typically in case the weather outside gets too warm for the more efficient cooling options to work effectively. Some cooling systems actually have multiple cooling technologies built in, and then cost functions within their controllers to help select the most efficient and effective mode of operation depending on the ambient conditions outside. So next we'll move on to looking at how a warming climate will impact energy and water use, and the data center more generally. So to reject heat to their surroundings, all of the cooling systems I've mentioned rely on a temperature differential between the working fluid and the ambient air. This is the case whether the working fluid is air, water, or refrigerants. And the temperature at which air can leave the heat exchanger that's rejecting the heat to atmosphere is limited both by the temperature of the working fluid entering the heat exchanger and by the design of the heat exchanger. So as the ambient temperature increases, the possible increase in air temperature through the heat exchanger is reduced, and so is the amount of heat that can be transported away per unit mass of air. And so for a fixed rate of heat rejection, as the air temperature delta reduces with increasing temperatures outside, we actually have to increase the mass flow rate of air through these heat exchangers. And that, of course, means increasing fan speeds to increase the fan flow rate. And as a result of fan laws, the power use actually increases with a cube relationship to fan speed. Adiabatic or evaporative cooling is often used to help reduce the temperature of incoming air. Water is evaporated naturally into the airstream, and the heat of vaporization for that evaporation to take place is taken from sensible heat in the air, leading to a reduction in temperature, which can help to maintain the temperature differential between the working fluid and air that I mentioned on the previous slide. But it's worth noting that this is limited by the ambient humidity. So higher humidities leave less capacity in the air for further water uptake, and so less capacity for evaporative cooling. In any case, this process, of course, uses water, as we can see on the right. And the water is often taken from processed sources, meaning that it already has embedded energy. And when it's rejected to the atmosphere with the airstream, it's obviously made unavailable to other consumers. And I think that's a particularly pertinent point in terms of heat waves, because during a heat wave, the adiabatic cooling systems are more likely to be in use for long periods. And that's actually going to increase the demand at a time where there's generally going to be increased scarcity. Now, as ambient temperatures increase, it may actually become necessary to increase the temperature of air being supplied to IT equipment within the facility. Now, that could be because increasing power and water usage and costs become unattractive, but it could also be because the cooling plant actually simply cannot deliver the required internal air temperature anymore. Now, IT equipment can typically accommodate higher inlet temperatures than are found in data centers, but at a cost. So higher inlet temperatures result in IT equipment drawing in more air, as illustrated on the right on this slide, where we see flow rate per unit computing power actually increasing as the inlet temperature increases, which of course increases energy use of the fans on board on the IT equipment. But the higher inlet temperatures also lead to increasing IT equipment failures. Interestingly, there are actually some data centers in equatorial regions where they accept the trade-off of having a higher failure rate of their IT equipment in order to reduce their energy and water use. But that's, at the moment, that's relatively unusual because it requires a very carefully designed IT system so that a failure can take place safely. Now, the graph on the right from an Atrey statistical analysis shows us how likelihood of failure rises with increasing inlet temperatures. So whilst there can be a financial trade-off, as I mentioned just now, between the cost of failing IT equipment and the operating cost of a cooling system, it can't be ignored that increasing IT equipment failure due to the increased inlet temperatures will result in more natural resources being used to build the replacement equipment, and also, of course, more e-waste coming out. So as well as IT hardware replacement, increasing temperatures could well result in cooling systems having to be replaced as they become unsuitable for locations as the local climate warms. And also, it's worth bearing in mind that cooling equipment that is working at the upper end of its design envelope will require more frequent replacement of parts. So this all results in increased end-of-life waste, increased use of natural resources for construction, and increased embedded carbon from the energy that's used during that construction. Now, due to heat island effects, data centers in urban settings are at an increased risk from these challenges, as the increases in ambient temperature will be amplified. Now, this could affect on-site enterprise data centers, which are where companies have their data center in their own building, and urban co-location data centers, where companies have their IT equipment in a shared space close to their offices. But there's also a general trend within the data center industry towards what's referred to as an edge data center, which is a data center on the edge of the network, which is far from a large-scale hub data center that does the majority of data processing, but close to the population that are using the services. And these will be exposed to increased risk and are actually expected to increase in number in coming years. And what's more, the urban data centers will actually be contributing to heat island effects through their heat output, although it should be noted that this will be second order perhaps, because the main mechanisms for heat island effect, I believe, are more based on radiation. But it highlights the hidden cost of waste heat and a lost opportunity to use it as a resource. So this leads us into looking at some potential solutions and opportunities as temperatures rise. The majority of power supplied to a data center leaves as heat, and there's increasing interest in using it as a resource rather than treating it as a waste stream. Now, I've seen examples of heat being used to contribute to district heating systems, for biomass drying as part of biofuel production, to help with heating greenhouses for food production, and for regasification of liquid natural gas, which our first speaker probably has much more expertise than me on. But most of these have been trials or experiments, and often the quality of heat is a limiting factor, which is to say we have heat being transported away from data centers in relatively high volumes of fluid, but at relatively low temperature, where typically high temperatures and lower volumes of fluid would be preferred. And that's basically because higher temperatures mean that there's a better temperature gradient available for the processes that you might want to reuse the heat in. So actually increasing the operating temperatures in data centers could make the waste heat more useful. Use of liquid rather than air to transport heat away from IT could also help to improve the quality of heat to facilitate its reuse. Air cooling is currently dominant in the industry, but liquid cooling strategies such as immersion cooling and direct-to-chip cooling are growing in popularity. So the image on the right here shows an example of direct-to-chip cooling, with liquid piped directly to and from processing chips to carry the heat away. The physical properties of the liquid used are favourable for heat transport, and the supply temperature of the cooling medium can be higher with liquid cooling than when using air. So this presents an opportunity to extract higher quality heat for reuse, but will also actually make cooling easier than when the heat isn't being reused, because with liquid cooling you can typically use a higher supply temperature, and as a result it's much more viable to use liquid to air heat exchangers to reject that heat to atmosphere as the external temperature increases, which will help us to avoid use of energy intensive mechanical cooling and the associated refrigerant with high global warming potentials. The move to liquid cooling has actually seen an increasing engagement between the IT equipment manufacturers and the data center operators. And fundamentally, data center design and operation reflects the needs of the IT equipment that the manufacturers produce, and changes to the design of computing hardware could potentially help us to accommodate the increasing ambient temperatures. So for example, increased temperature tolerance of IT could help to prevent the increasing failure rates at higher supply temperatures that I mentioned earlier. Reduced power demand through improved computing performance per watt could help reduce the power draw of the IT equipment and the overall cooling requirement for an IT workload. And finally, avoiding unnecessary increases in power density and reductions in size could help. I mean, I think it's important to acknowledge that manufacturers claim there's a market demand for this trend, but increased power density and reduced form factor can make the use of higher temperatures in air-based cooling much less viable. So avoiding this will make it easier for existing cooling systems to support new IT equipment, avoiding the need to replace the cooling systems. But we shouldn't, from a data center industry perspective, we shouldn't really look at putting the responsibility for changing design practice solely onto the IT equipment designers. I think we, within the data center industry, also need to change our approach. Currently, it's common to use historic weather data as the basis for designing a cooling system for a data center. For example, basing peak design temperatures and the degree design days on the past 20 years of weather records for a location, rather than looking at what we can anticipate for the future. So really we need to look towards predicted trends so that our design can be future-proof. And some major data center operators have begun to do this, but it's really not common. And so I think one issue in the adoption of it is that, as was mentioned very early on in the event, predicted data has uncertainties in it, which historic data doesn't. But I actually think that this could present an opportunity, because if data center operators have based their designer and invested in a particular predicted scenario, then it becomes in their interest to help ensure that that scenario comes to pass, rather than one where temperature increases are more significant, because this will help them to achieve their expected operating costs over the lifetime of their data center and avoid the capital expense of upgrading their systems to accommodate more significant temperature rises. So I'll leave you with that thought, whether the uncertainty involved in designing based on predicted weather trends can actually help to incentivize data center operators and other economic actors to act and advocate to limit climate change. So that brings me to the end of the agenda. Thank you for your time and your attention.
Thank you. It was a very good summary and on what data center sees in the future, and where the climate action, climate change may cause an challenge. So we have a bunch of questions on the Google Sheet, and we have about 5 minutes as per my message received. we have, I think I had one and Professor Atrey had one for Masaaki-san. Priya,
Yes, sir.
You,
can you bring up the Google Sheet?
Okay. Just a second, sir.
yeah.
I can't share it, so that's why. I can read it instead.
Yes, sir. That would be good.
The question for the LNG is what kind of heat exchanger is typically used for LNG and other fluids in the systems that you had discussed? Is the question for.
Could you repeat the question?
What kind of heat exchanger
Okay.
is used for LNG?
Okay. In general, the heat exchanger is quite various types of the heat exchanger. It's depend on the purpose of the achieving temperature. Sometimes in case of the seawater, the vaporizer, they use very much expensive material to prevent the corrosion or any the temperature difference in between the LNG and the seawater temperature. It's really depend on the services.
Okay. Thank you. There was one question for Dr. Gharpure from Snehal Gaikwad. Dr. Gharpure?
Yeah, tell me.
So the existing infrastructure, which is not designed and built, considering the climate change impact, what options other than retrofitting do we have to make climate resilient is the question.
Yeah, what was the first part? The existing infrastructure is not designed? I mean, what was the first part?
For the existing infrastructure, which was not designed for the climate change impact, is what retrofitting options are available?
Yeah, so the predominant focus is to reduce or to conserve the energy. That is one. So how do we reduce the extent of the energy consumption in the existing building? So as my presentation pointed out, treating of the facade, treating of the roofs, treating of the surroundings, that itself can add to a lot of reduction in the heat gain which the building has from the surroundings. And if we reduce the heat island effect with the proper treating of the surroundings of the buildings, even the existing areas can be drastically improved. Did I answer that?
Yeah. Thank you. I had one for Mr. Matthew. PUE, power usage effectiveness, is temperature dependent. And typically, I know this is widely accepted in data centers, and people can easily manipulate PUE by moving the infrastructure cooling equipment to the hall and claim a better PUE, even though PUE served its purpose in terms of bringing down energy consumption, overall energy consumption in a data center. But now people claiming 1 and 1.02 may have issues because they have probably, some of them may have played a game to move the fans. So how could we address? I mean, there are other metrics. They all have equally other issues like total usage effectiveness and so on. So is there any comment from your end where you see, because I think these metrics served its own purpose, now they have to be reevaluated with the climate change. And you bring up the point at the end of your presentation as well. So I just wanted to hear your perspectives.
Yeah, so I mean, I think since power usage effectiveness was first introduced, there's been an ongoing debate about how easy it is to abuse it as a metric. So I'd agree with you very much that is an issue underlying it. I think in terms of how to move forward and improve the KPIs that we have available to us within the data center industry, I think really what we need to move towards, and there are actually new KPIs coming out in one of those ISO standards that I mentioned during the talk, that look much more actually the efficiency of IT equipment. And I think to my mind, what we're probably going to really drive towards is, rather than looking at what the overhead energy use is compared to the IT system energy use, we'll actually start looking at what the overall energy use is for a facility compared to the useful computing services that it's providing. And that's what we really need to move towards. Because in terms of looking at the efficiency, it isn't normal to say how much energy do I use for one thing and how much more do I use for another. Typically, what we talk about with efficiency is how much of the thing that I want out of a system am I getting compared to how much energy we're putting in. And I think by doing that, we'll avoid the issue of people, for example, like you said, moving energy use into the white space, into the data hall. Because actually what we'll be doing is saying, how much energy am I having to use in order to provide this computing service, rather than comparing relative amounts of energy. I hope that answers the question.
Yeah, thank you. Yeah, that makes sense. So that I think we should move to the other main session now. Thank you all for presenting, and I personally felt those were very wide and engrossing topics to cover, even within such a short duration. Typically, in a big conference, you have all these 1 hour presentation. Within 1 hour, now we were able to get the gist of it, and I'm happy to be part of this and to be learning with you. Thank you.
Thank you.
Yeah, thank you to you also for moderating.
Desalination type has been proposed, especially near regasification plants. Water desalination. Has there been any successful studies? Is something from
water desalination.
Yes.
I have not heard about the case of the water desalination with the use of the LNG. No, I don't have the experience with this kind of application.
Okay, thank you. I guess we'll just have to wait. Thanks again for your time. And if there are other questions from the participants, please, you're more than welcome to put them on the chat, on the Google Sheet, or even speak out.
One comment from the Mr. Ebina to Matthew. I think the LNG is the vaporization is very much a good match with the IT sector. Data center is going to be a perfect match, and also IT industry, if they use the cold heat control, it's really the idea.
Yeah, I agree. I think there's really a good opportunity for synergy.
Yeah.
Really good opportunity.
Yeah.
because the heat is also low quality heat, but the energy, cold energy comes in, so that allows a good.
It's an exchange of services. An exchange of
Right.
services. Yeah.
Yeah.
Thank you all. I think looks like we are moving out of this session into the main session. So thank you.
Thank you.
Thank you.
Thank you very much.